So what do we need compositions for? Compositions are very good at helping us figure out if two functions are inverses. Because two functions are inverses if and only if, you remember that from geometry, right? If and only if, and that is a biconditional, yes, that's exactly right. F of g of x is equal to g of f of x, and both are actually equal to x. So let's see if our two functions here, f of x and g of x, are inverses. F of x we're going to do in green, and g of x in orange. G of x is 1/2 x plus 6, and then we take that input for f of x, multiply it by 2, subtract 6, and now let's go and simplify this. Distribute our 2, we get x plus 12 minus 6, which is x plus 6. And x plus 6 is clearly not the same as x. So these two are not inverses. We don't even have to bother checking out the other way because it has to work both ways. And if it already didn't work the first way, then it doesn't matter. These two functions are not inverses. Let's look at the other two. F of x we're going to do in green again, and g of x in orange. G of x takes our x, adds 2, and then takes the square root of that. And f of x takes this input, squares it, and then subtracts 2. Now our square root and our square cancel each other out, so we have x plus 2 left from the parentheses, minus 2, and that is equal to x. So that checks out. Now we need to figure out the other way around. First f of x, which is x squared minus 2, and taking that input, adding 2 to it, and taking the square root. Now first we're going to simplify underneath our radical. X squared minus 2 plus 2 just leaves us with x squared. And now we're taking the square root of x squared. Two operations that are inverses cancel each other out, and we end up with x. That checks out. Both ways checked out. So yes, these two functions are indeed inverses. Now let's talk about how can we find the equation of an inverse function. And the way we do this is by performing two steps. First, we have to switch the x and the y in the given function. And then we solve the new equation for y. So here we have our example. Y is equal to 2/3 x cubed minus 4. And now we're taking the x and the y, and they're just going to switch places, which now gives us x is equal to 2/3 y cubed minus 4. And this equation we're now going to solve step by step until we end up having y again all by itself. Okay, so let's add 4. We get x plus 4 is equal to 2/3 y cubed. Next, we want to get rid of our fraction, so that means we have to multiply both sides by the reciprocal, which will give us 3/2 x plus 4 is equal to 3/2 times 2/3 y cubed. On the right, the two fractions are going to cancel each other out. We're left with only y cubed. And now we're going to take the cube root of both sides to get the cube root of 3/2 times the quantity of x plus 4 is equal to the cube root of y cubed. And again, those two inverse operations cancel each other out. We have y on the right, and on the left I'm going to split what we have underneath our radical. So we have the cube root of 3/2 times the cube root of x plus 4. Since in our next step we want to graph this, and our first part here is our dilation, I'm going to go ahead and find the decimal value of that. Otherwise, you wouldn't have to do anything else from this step on. The cube root of 3/2 is 1.14 times the cube root of x plus 4 is equal to y. And that is our inverse function. And if we now remember what we said back in Unit 1 about inverse functions, when we graph them, they have to be reflected. And now we're going to go ahead and graph our two functions in our coordinate plane. Let's start with our cubic function. We had 2/3 x cubed minus 4. In other words, we have to go down 4, and our dilation is 2/3, so 1 to the right and 2/3 up, 1 to the left, 2/3 down. And here goes our cubic function. And for our cube root function, we have h is -4, going 4 to the left. Don't have to go up or down. But our dilation is 1.14, so a little bit more than 1. In other words, we're going to go 1 to the right, a little bit more up, 1 to the left, a little bit more than 1 down. And remember, that's a curve which goes sideways, wiggles through the vertex. And here are our two functions. And if we remember what we discussed in Unit 1, two inverse functions have to look like they have been reflected over the diagonal y is equal to x. So now let's put that diagonal into our coordinate plane. And as far as I can see, that's exactly what this looks like. So these two are indeed inverse functions. We have proven it algebraically, and we have proven it graphically. Well done, you guys, and I will see you in class.